thank you in particular also to Roland, who is somewhere here, I guess. Very pleased to be here. And I'd like to thank all 3 laureates as well. And I think it's great that this Ludin Symposium is this year extended also to younger people from the Nordic countries. Very long title. I'm going to explain it in just a wee bit what it's all about, but I'd also just like to take an opportunity to say, who are we? So I have a small group at the Technical University of Denmark. It is situated just north of Copenhagen, some 10 kilometers north. And we work on a variety of different things. Over the past 4 or 5 years, I've been very interested in seeing how we can do mean field theory differently. So I've devised some theories for partitioning, say, molecular properties calculated at the mean field level, so Fock or quantum DFT, into local atomic properties. I extended this to the excited state as well, so that we can actually look at local contributions to optical properties. Most recently, my PhD student Luna has extended this also to periodic simulations. What can we do with this? We can actually look at how these local properties derived from local electronic structures, how they change as molecules undergo chemical transformations. And Frederick, my PhD student, has also been interested in looking how we can apply this to train machine learning models. So in particular, atom-based neural networks. So looking at how individual contributions, how the uniqueness of local electronic properties, how they change across chemical compound space. Just this morning, he had a new paper out in which we look at how transferable atom-based neural network, so Bella-Parinello type models, how transferable they are as you move from one part of chemical space to another. And in this paper, we also apply something called adversarial validation to actually compare what is the similarity between your training set and your test set, and how much faith can you have in actually having a good machine learning model trained on a given part of chemical compound space. However, now, okay, so just to round off things, I have a PhD student who's also looking at how to actually look at local electronic properties also in condensed phases. Because if you can decompose a supercell calculation into local atomic properties, you can cluster these among the monomers, for instance, in a condensed phase, and then you can derive local properties also for bulk phases. Okay, so today I will not be talking about mean field theory, I will not be talking about machine learning, I will be talking about ways in which you can incrementally approximate the numerically exact solution to the electron exploiting equation. So from one end of the spectrum to another. And this is a topic I've been interested in ever since I did my PhD there. I did a couple cluster perturbation theory. But when I started doing my first postdoc in Mainz and my second one in Bristol in the UK, I've been working on what we call many-body expanded full CI theory. And I was invited to do a perspective on say, high accuracy quantum chemistry some few years ago. And in this paper, I argue, I'm not the first one to do that, but I'd say in its benchmarking capacity, modern full configuration interaction has inevitably been transformative in helping shape the field as we know today and really manifest theoretical chemistry as a scientific discipline with immense interpretative and predictive powers. So I actually think that full CI theory is as important today as it has perhaps ever been before. So I'll give some perspective on that later on. Okay, so as I said, over the past 5 or so years, I've developed this theory called many-body expanded full CI theory. So in a sense, properties at this level of theory, be they energies or dipole moments, they can be obtained by correlating all electrons of a given system independently and in succession. So you do this by means of many-body expansion. So in a sense, you have your target property here, and you can just divide or partition this into an incremental sum in which you have some contributions here, and then you have increments, so like residual contributions added on top of that. I will today just be focusing on ground state energies, but you can also extend this to excited state energies, dipole moments, transition state dipole moments, and so on. So what do we actually do? We start by dividing the total space of molecular orbitals into what we call a reference space. So this is the subspace of molecular orbitals, which are always included in all the individual CAS-CI calculations. So these truncated full CI calculations in a truncated space of molecular orbitals, you always include all of these MOs in the reference space. And then you have an expansion space, which is just all the orbitals not included in the reference space. And how you recover the correlation energy is simply by recovering this residual correlation, which is not already captured by doing a CAS-CI calculation in this reference space up here. So this is actually not a new theory. So if you look at your total molecular space, orbital space, as consisting of a virtual space and an occupied space, then you could imagine having a reference space which includes all the virtual MOs, and then you let your expansion space be the subspace of occupied orbitals. And then when you incrementally include more and more occupied orbitals, you will, at the end of the day, arrive at the full CI level. And this is, as I said, very old theory. This was pioneered by Nesbitt back in the 60s. And around the same time as I imagined I would do this in my postdoc, Paul Zimmerman in Michigan, he proposed exactly to do this. So that was a bit of a letdown. This is to show how it converges. So this is just a small toy system, N2 and a small basis set. You have 10 electrons and 16 orbitals, but you only have then 5 occupied orbitals. And you know, when you account for all single orbital contributions, pairs of occupied orbitals, and so on, you inevitably get, at the end of the day, to chemical accuracy. But if you look at how many determinants you have in your individual CAS-CI calculations, then you actually have to do, even for a small system like this, individual CAS-CI calculations that have more than 1 million determinants in them. So if you do it this way, you'd have a very poor scaling with the number of orbitals, although you have a decent scaling with the number of electrons of your system. So what we proposed in collaboration with Jürgen and Mainz is to flip this on its head. So your reference space is now all the occupied orbitals, so you always correlate all the electrons, but you do so in a space of successively more and more virtual orbitals. And how does this converge? Well, convergence is perhaps a bit poorer, but if you look at how many determinants you have in the largest CAS-CI calculation needed to arrive at chemical accuracy, you see that this is cut by more than an order of magnitude. So now you'll have a decent scaling with the number of orbitals, but since you always correlate all the electrons among each other, you'll have poor scaling with the number of electrons. So, well, you don't need to base this on the Hartree-Fock reference. You get some improvement if you base it on a CAS-SCF reference space, but at the end of the day, you still have to have rather large CAS-CI calculations in order to reach chemical accuracy. So finally, you could say, well, I don't have a reference space, okay? So my expansion space are all the molecular orbitals, all the occupied and all the virtuals. And in a very unbiased manner, I just start to have pairs and triples and quadruples of these orbitals. So then I'll have a variable number of electrons correlated in a variable number of orbitals. And you can see now convergence is a lot worse. However, you only need something like 1,000 determinants in your largest CAS-CI calculation needed for achieving chemical accuracy. So if you do this, you'll now have decent scaling with the number of orbitals and decent scaling with the number of electrons. And all of these individual CAS-CI calculations are embarrassingly parallel to evaluate. So this is a very parallel efficient scheme, right? We've scaled it up to 25,000 cores without a problem, really. So it's very suited towards HPC. So 4 years ago, we teamed up in a large international assessment, so saying, okay, we have all these approximate full CI methods. Let's try and do a blind challenge. Okay, so we presented them with a structure of benzene and say, please compute the correlation energy of this benzene structure, frozen core approximation, in a double zeta basis set. It's in a sense, it's a very standard calculation, but no one knows the answer, right? Because an exact full CI calculation involves something like 10 to the order of 36 or something like that determinant. So you could never ever do an exact full CI calculation on this system. But you have this myriad of approximate full CI methods. So how do they compare? So this is our result, doing an MBE full CI calculation on the system. So we have a reference space of all the occupied and the virtual valence pi space orbitals, and we converge to this number. So what does this number mean? Well, you have to compare it to all the others. So here you have CCSDTQ in itself, a couple cluster calculation with full quadruple excitations is for benzene, this is like the biggest you can do at this level of theory. But you would also expect that this is more or less the exact result. Everything beyond quadruple excitations in couple cluster would be very minor, very marginal, because this is a system dominated only by dynamic correlation. So this is supposedly very, very close to the exact result. We see a large spread. So here you have like selected CI models, here you have stochastic full CI models, DMRG, and here you have our results. And this is a reduced couple cluster model from Janus group. So you see a large spread, but you see perhaps some consistency here and some convergence towards the result of, say, minus 863 millihartz rate. So what have we done since then? It had a bit of a hiatus because I started doing mean field theory, but now we picked up on the idea again. So quite recently, we have extended this method so now you can actually attach error bars to these MBE full CI results, which is quite meaningful, and not many models allow for doing so, but instead of just reporting a single number for what you think is the correlation energy, actually being able to attach uncertainties to this, I think that's very important. Also, detecting active spaces not only within MBE full CI, but in active space methods more generally, is something which we also propose a new way of doing based on quantum fidelities in this paper. We've also extended it to CAS-SCF in collaboration with Filippo in Pisa. But what I'll be talking about today is how to utilize non-abelian point group symmetry within this MBE full CI model. So here's the general idea. If you look at a system like benzene, you'll obviously have pairs of orbitals which are related by point group symmetry. So the correlation energy you calculate in this pair of orbitals is obviously the same as within this set of orbitals. So here's the procedure for how we implement point group symmetry. We loop over all orbital combinations, and we denote this as what we call the grand list. And then we apply symmetry operations to each of these orbitals, orbital tuples, because it's like pairs and triples and quadruples and so on of orbitals. And we determine what is the greatest orbital tuple, the greatest orbital combination on the basis of lexicography. And then we consider only this particular tuple for a set of symmetry equivalent orbital tuples. And these then form what we call the petit list. And we call it the petit list because this is a very, very old theory for how to handle point group symmetry for AO integral evaluations. But in a sense, this applies to any kind of object, orbital object. So in this case, an MBE increment. So it's quite easy to generalize. And it's a very elegant theory, but it's been sort of like just hiding there for the last 50 or so years. So in order to do this, you need to be able to have objects, in this case, MBE increments or orbitals, which are related by exact symmetry properties. So that means we generally work in basis of spatially localized orbitals. To the eye, these look to be related by symmetry operations. However, they are not exactly related by symmetry operations. So they don't fulfill these exact symmetry features which are needed to use this petite list machinery. So last year, I worked with Jonas Greiner. He was a PhD student in Mainz, and he's now a postdoc in my group, on actually symmetrizing localized orbitals. So, well, a symmetry operation applied to an orbital will give you a new orbital, and we generally divide these into 3 classes. There are those orbitals, when subject to a symmetry operation, are invariant. So these are what we call the symmetry invariant orbitals. There are those that are symmetry equivalent if you do a C2 operation here. And then there are those that are non-symmetric. So the idea is now to design a cost function that will impose a penalty whenever certain blocks of the matrix representation of this operator fail to vanish, and it itself has to vanish whenever all symmetry constraints are fulfilled. So what do? You start by forming this matrix which holds the absolute value of G summed over all symmetry operations. So that gives you a heat map like this. And independent blocks of this matrix up here will be invariant under all symmetry operations. And this block structure can be revealed by using something called the reverse Cauchy-Marquis algorithm. So it simply just recovers the block structure which is not visible here, but in a sense the orbitals used to generate these 2 heat maps are exactly the same. Now the thing is that you then optimize a tailored cost function which finds unitary rotations which, when applied to these orbitals, render contributions to this G sigma matrix insignificant whenever they whenever they fail whenever they fall below some threshold, right? So in a sense, what you do in going from here to here is that you enforce these exact symmetry features among the orbitals. And these are Pipec-Messier orbitals. These are Foster-Boyce. To the eye, the Foster-Boyce operations have much less symmetry than the Pipec-Messier orbitals, but at the end of the day, you can compress this full set of canonical orbitals, full set of Foster-Boyce orbitals into only 8 symmetry-unique orbitals. So if you take a system like Buckminster-Fullerene here in the icosahedral symmetry, in the symmetry-adapted canonical MO basis, you'll have something like, you'll have more than 800 orbitals. You can compress that into only 18 symmetry-unique Pipec-Messier MOs, and only 14 if you do it in a Foster-Boyce basis. So this is a compression of, say, 2 orders of magnitude. And then you can start doing calculations only in this set of orbitals, which is what we do in MBE-FCI. So these are just results showing how much you can save in an MBE-FCI calculation if you enforce these symmetry features. And the higher you go up in point group, the more you generally save. So in the TD point group, you can save something like 90%. And this is pretty agnostic with respect to what kind of basis that you're using. So now we've revisited the benzene results in the double zeta basis. These are the old results that I showed earlier. So embarrassingly enough, we were the entry in this bind challenge that by far used the most computational resources. We used almost 2 million core hours just to arrive at this single result. Most of these selected CI methods are much, much cheaper. They take maybe 10,000 core hours to arrive at a result, but the result might be rubbish, okay? So what you can do is that you can use MBE-FCI not to recover the full correlation energy, but rather the gap correlation energy between some intermediate model and then full CI. So you can actually base these MBE full CI results on high-level copper clusters. That's what you actually recover in the MBE full CI result calculation is the gap in energy between, say, CCSTT or CCSTTQ and then full CI. So it's a much smaller energy which you have to recover. And if you do so, you get these two results. So this is when based on CCSTT, and this is based on full Q. And timing for this is, you save some 3 orders of magnitude in timing. And this result, which you expect to be the most accurate of all of these, you see it aligns really well with the full Q. And just a comment saying that this parenthesis Q, which if you go to larger basis sets, this is the most pragmatic you can do. It's a bit below the full Q, and you would expect if you do it in a triple Zeta basis, it will be the same. And just to say, in these calculations, you save some 90% of having to do all the calculations. So only some 10% of the calculations actually needed. So these are the results in the triple Zeta basis. Again, the best you could do is this parenthesis Q. It's expected to be slightly below full Q, which is expected to be more or less equal to full CI. And we get a result which is just slightly above. So we would say that this is definitely within chemical accuracy of the correlation energy of benzene in a triple Zeta basis. This is the best literature result you have. This is auxiliary field QMC, and you can see that it's pretty far off what we expect to be the most accurate results. And again, you can skip like 250 million calculations if you use symmetry. Okay, so what are some of the future perspectives? Well, I'd say that MBE full CI is among the most successful contemporary near-exact approximations to what you would say is a standard full CI. However, the number of independent increment calculations will still continue to grow, even if you enforce symmetry. So for this reason, we would have to maybe use what we call overlapping clusters of molecular orbitals, leveraging some of the ideas for John Herbert's group on generalized MBEs. But we're also working on improving how we account for spatial locality. So there will be a huge number of increments that you won't have to do simply because when you work in a localized basis, there will be marginal correlation between individual orbitals when they're far apart in space. Okay, these are just some acknowledgements. And then I too will end by saying that we also have a satellite meeting, not coinciding with Susie's, but ours is just in the days leading up to the WATOC meeting in Oslo. It will strictly be on electronic structure theory, and it'll be at the Carlsberg Academy, which is one of the nicest places in the greater Copenhagen area. So I'll end with that, and then thank you.
Excellent. Thank you very much, Janus. And the big question is whether the only beer they serve is Carlsberg, but that's for later. Do we have questions in the audience here? Anyone? Here. Joe, go ahead.
So you talk about symmetry. Tell me about what happens when I lose a little bit, small distortions. What goes on?
So if you assume symmetry, but you don't have exact symmetry in your MO basis, very quickly on, because of the recursive nature of how you do this MBE, your error will just explode. Okay? So that's why, so you can assume this, you can use the petit list machinery and all that, but your errors will be immense very early on. So that's why, to begin with, I have to admit, we looked at these orbitals and then we said, well, they look very symmetric. But just tiny, tiny, tiny differences that will explode. So I will also say that we just minimize some tailored cost function. But we do that after we've spatially localized the orbitals. However, we have checked, and you don't really lose locality in doing so. But if you did it the most elegant way, you'd set up a Lagrangian such that you sort of optimize both locality and symmetry at the same time. But I will say that you don't really lose any symmetry, you don't really lose any locality by enforcing these symmetry features.
And we have a question here from Henrik.
A little bit more chemical question, organic chemical. If you would go down to cyclobutadiene, which is then anti-aromatic compared to benzene, which is aromatic, how can you see any trend in the extent of the electron correlation? Have you looked?
No, I haven't looked at it, sorry. It would be interesting to look at, though, but I haven't looked at it.
Yeah, it would computationally be a little bit more demanding because you have static electron correlation effects.
But then it's just a matter of actually choosing the most appropriate reference space. Mm-hmm. As I alluded to, I didn't go into detail, but now we have like an automatic way of choosing the best active space. So in our case, the best reference space. So it's definitely doable.
Yes, yeah, it would.
Other questions? In order for me maybe to remove a misunderstanding. Oh, I'm sorry, Roland, go.
So your approximation, you're trying to get out the full CI result. Is it invariant to any orbital representation you have? Because
yes. So, I mean, at the end of the day, you hope to converge your results tightly enough, right? So then it should be agnostic.
Yeah.
There will be orbital representations that are better than others, which is why, we tend to use localized orbitals.
Right.
You could also do this in a canonical orbital representation, but your convergence would be really slow, okay? So we use localized orbitals to get the fastest possible convergence, and then, we play tricks on this because also what I said at the very end is that we'd like to screen away, avoid having to do calculations because we know that there will be only a marginal correlation between orbital pairs or orbital triples. And this will only hold true in a spatially localized orbital basis. But yes, the convergence will in general be different, in any choice of orbital.
All right. Thank you.
So you have orbital variance, but it's a good thing here.